Hi, I'm Hannah. I'll be presenting about my project on improving a cancer drug called Gefitinib, specifically making it more safe and aiming for both oral and IV in administration. So for the background, non-small cell lung cancer accounts for 85% of lung cancer. Gefitinib is a drug used to treat non-small cell lung cancer patients with an EGFR mutation. And EGFR stands for epidermal growth factor receptor, which is a crucial protein that controls cell growth. And gefitinib works by blocking this receptor so the cancer cells stop growing. However, there are two major problems with gefitinib. First of all, it can damage the liver, which is called hepatotoxicity or liver toxicity. And secondly, it can only be taken orally. So in my project, I wanted to create new derivatives, which is by modifying the structures to improve the efficacy of gefitinib that makes it keep working against cancer and causes less liver damage and possibly allow IV injection as well as oral use. To do this, I used computational modeling tools to create five derivatives. I used Protox 3.0 to predict toxicity and log P values, which I'll explain later on. I used ChemDraw and PubChem Sketcher for structural modifications. I also did other analyses like LD50 binding affinity polar interactions and so on, but I won't cover those today for the sake of time. Um, and this page shows the structure modifications like the derivatives I made. Let's go into toxicity predictions. The red bars indicate active toxicity endpoints, and the green bars indicate inactive toxicity endpoints. More green bars mean that the drug is safer, and a darker color means the prediction is more confident. And this page only shows gefitinib D1, 2, and 3, I think. And wait. And the next slide shows D4 and 5. Um, Here are the results for toxicity predictions. All five derivatives reduced liver toxicity, which was my main goal of doing this research project. And D5 had the strongest prediction with an 82% chance of no liver toxicity. However, immuno and respiratory toxicities remain high for most derivatives. And D3 was the only one that significantly lowered immunotoxicity from, let me see, 0.99 to 0.89, making it the least toxic overall. Then, wait, okay. Then I looked at log P values. The value tells us whether a drug dissolves better in water or oil, which is very important for figuring out if it can be injected or swallowed, like taken orally or through IV injection. The ideal log P value for um, drugs that can be used both orally and by IV is about 1 to 3. So D2 had the best log P value in that range, meaning it could work well both by mouth and by injection. And D3 and 5 had very low log P values, so they are good for IV use, but they may be too hydrophilic for oral delivery. And this slide shows the limitations of my study. Uh, the major problem I found was that immuno and respiratory toxicity remain high. So, future designs may need to combine anti-inflammatory strategies or entirely new substructures in the modification process. And also, even though liver toxicity decreased, the confidence levels for some predictions were low. So, lab testing like in vitro hepatocyte assays is needed to confirm these results. And I didn't make any changes to a specific part of gefitinib structure called the propylmorpholino ring, which might also affect toxicity. That's another area we can explore in the future. So to wrap up, D2 had the best balance in reducing liver toxicity, having a good water solubility, binding effectively to the EGFR target and working well for both oral and IV delivery. However, D3 had the most potential in future development because of its lowest immunotoxicity. It can bind to the same target residuals as the original gefitinib, which means that it can function almost the same as gefitinib. But it also has a high predicted acute toxicity reflected by the LD50 value, which I didn't show in this presentation, and further studies are needed as well. So all five of my new derivatives showed some level of improvement in toxicity and solubility compared to the original drug. This shows that we can use structure-based design to make better cancer drugs, but future steps will include lab testing, clinical validation, and exploring new structures to better achieve these goals. Thank you.